Hi guys. Oh god, I'm so tired. I hope you guys are doing okay. So this is one day before the maths exam. Um, I'm kind of stressed out. But yeah, anyways. This is on the specimen paper. So I've done the questions on the 2020, I don't know, whatever the specimen paper was. And I've given answers for them. Full disclosure, for B2, the final part of B2, I couldn't get it. I just couldn't manage it. If anyone else can, please let me know. Just give me a text or something like that. But this is what I've got so far. Anyways, I've also, hold on, where's my, yeah, there it is. So there's the paper. So let's go through everything bit by bit then, okay? So I'm just going to explain this. So we've got the following matrix here. It asks us to sketch in the UV plane the set of points which A has no inverse, okay? Now, if you guys remember, an inverse matrix does not have a determinant of 0. So therefore, a matrix that has no inverse has a determinant of 0. So what we can do is we can calculate the determinant of this in terms of u and v and set it equal to 0. This gives us 2u squared minus 6u plus 4v, okay? And setting that to 0, we get 2u squared minus 6u plus 4v equals 0, which we can graph out in the UV plane. If we treat u as x and v as y, we can sort of graph it out. Here I've got this graph. If I enlarge it, you can see that it passes through the points 0 and 3, and it is an inverted graph. So hopefully that's helpful there. Okay. I also rearranged it into v equals 1.5u minus 0.5u squared, because that's technically the same thing. So these points fulfill this axis. Now, the next bit says that hence or otherwise show that when v is larger than 9 over 8, A has an inverse for all values of u. You can actually see this through this. You can see the peak here is at 9 over 8. So anything above that, there would be an inverse, because it would be impossible to have no inverse. Remember, these are the points that satisfy the requirement of no inverse, okay? Whereas any point in the white space will be an inverse. So any point above the maximum is going to have an inverse. So you can also test this by technically, yeah. What is it? Yeah. If you treat v as a constant instead, and then try to find the discriminant. So the discriminant will show you how many, if there was a possibility of having, hold on, the discriminant actually just give you this. So you can generally test if, how do I put this? Yeah, so kind of using the discriminant in this case, and treating v as a constant, would give you the range of values for which there would be no solution to this determinant equation. So there would be no solution. There would be no viable value of u for which there would also be a value of v that equals 0. So the core thing is that you want there to be no roots. So you're putting in that into the discriminant. What you get there is 36 minus 32v is smaller than 0, which rearranges into v must be larger than 9 over 8. So that's how it's proven. For this quadratic form, what you kind of want to do is think about it in a way, how do I put this? I have a bit, also I will publish my answers and the big formula sheet, as well as some other resources in the description below, so just in case you guys need that. Where's my quadratic form bit? Here it is. So this is, if you guys can see this is the matrix for generally third order quadratic form. And what you want to do is you want to split the number basically just in half, or you can do, well, I'll show you, okay? So for our first quadratic form, we have x1 squared, x2 squared, and x3 squared minus x2, x3. So this corresponds to putting a 1 in front of all the diagonal bits, and then x2, x3, as we can see from our little thing here, is the f value, so it's the bottom two here. And given that it sums up to -1, we need to put in an algebraic combination that sums up to -1. Obviously changing the balance of it. So what I've done here is I've done -1 minus a, and then a for the other one, because if I combine these, it becomes -1, and I can vary the value of a to vary both of those values, okay? So this allows me to see if a certain value of a would give me a certain determinant, which would make the matrix positive semi-definite instead of positive definite, okay? So doing this, you can calculate the determinant from it, which is a squared plus a plus 1, which gives you a positive value for every value of a, which is good. So given that we always have a positive determinant, I think, yeah, we always have a positive determinant, and we always have positive values on the diagonal as well. We have a positive definite matrix. I did see some people in the chat saying it was not positive definite or positive semi-definite. It was neither. But I'm not entirely sure about that perspective. From my perspective, it is positive definite. Obviously, if you oppose me, kind of sound like a fucking warlord. Just feel free to let me know, text me, and I'll just add an amendment. Anyway, the second quadratic form is similar, but it's going to be in a different place. So -2, this will go up here in the D area. I've done the same thing where I've done -2 minus a plus a. This is a determinant of a plus 1 squared, which is actually 0 when a is equal to -1. So this is going to be called a positive semi-definite because the determinant is not always positive, it is sometimes 0. So that's that. The diagonals are still positive though, so that's good. Alright, so that's A1, good. So now for A2, I heard this one's trickier. So to find the demand functions, what we generally do is we do a Lagrangian, okay? So a Lagrangian is usually used when we're trying to find demand functions. Now, other people may have been persuaded to use the Roy's identity, but there's no real way of getting this into a sort of an indirect utility function. There's no real way of getting it into an indirect utility function, so we have to keep it as this. So what we do is we do a Lagrangian, and we're doing the partial derivatives of x and y, rearranging for x and y. So you get, at the end of that, if you sort of look at this process of events here, you get alpha, also feel free to pause if you need to. We get alpha over lambda p and beta over lambda p. We add this back into our budget constraint, okay, and we get a value of lambda, okay. Then, because we need to get a value of lambda in terms of other things, that's the main point here. We don't want a value of lambda to just define x and y. You need lambda in terms of something else. So once we get a value of lambda, by inserting it back into the budget constraint, we can reinsert that back into these to get our demand functions. So you can see the demand function for x is alpha m over p alpha plus beta, and beta m over q alpha plus beta. Okay. Now we do the same thing for the second one, but we're going to slightly modify our equations. First of all, you can clearly see that v now has a gamma ln big L minus little l, which is fair enough. But now our budget constraint has two determinants of income, which is unearned income, n, and earned income, denoted by wage and labour. So we're going to denote that as WL plus M in our equation. Performing the same steps, you can see that we've performed the Lagrangian. We partially derive with respect to x, y, and L now, because remember we're looking at hours worked per week as well. We get these in terms of the constants and lambda, and then we're looking to find a value of lambda as well. So we reinsert these values into our budget constraint, and then we get a value of lambda out of it, and then we reinsert that value of lambda back again. So we can see then that we've got x is equal to alpha WL plus M over P A alpha beta gamma. Y is similar with beta and Q reversed, and L is big L minus gamma bracket WL plus M over W alpha plus beta plus gamma. This process I went through a bit fast, so feel free to pause on this. It's the same process as we've done before. But then if I rearrange what L is, I get LW bracket alpha plus beta minus gamma M over W alpha plus beta plus gamma. Now, the question asks us to assume that m is smaller than alpha plus beta WL over gamma, okay? So if m was truly equal to that, okay, then think about it. If I'm timesing this by gamma, okay, the gamma at the bottom cancels out and it becomes alpha plus beta LW, which is the same as the starter thing. What this would mean is that if m was smaller than alpha plus beta WL over gamma, then the numerator would be negative, okay? And having a negative hours worked would be implausible. So m must be smaller than alpha plus beta. Well, m must be larger than that because we cannot work negative hours. That's the main thing. All right, B1. B1, it was fairly easy for me. I don't think many people had problems with this. But just in case, let's go over it. So, this is a standard utility matching to budget constraints. We need to match the MRS and MRT, as we do usually. So what we need to do is we need to implicitly derive for both curves with respect to x1. You can generally find that quite easily with the budget constraint. The budget constraints, the budget constraints gradient is -4. Quite easy to find that out if you just sort of graph it out. But we need to implicitly derive the the utility equation, which would give you dx2 over dx1, which is sort of like dy dx, is equal to -20 over root of x1. Okay. Then equating these, you would get x1 equals 25. So that would be the optimal amount of x1 to buy at every utility level, because our derivative for dx2 dx1 did not contain a y. Okay, so we don't really need to worry too much about it. So this says that at the optimal point, x is equal to 25. So if we have a budget constraint of m equals 300, then looking at our budget constraint, then if we insert 4 times 25, which is 100, plus x2 equals 300, so 100 plus x2 equals 300. So x2, we're going to be buying 200 of that. Okay. So that's the optimal amount to buy, okay? However, for the next one, we have m equals 50. Now, to buy x equals 25 at m equals 50 would be implausible because we can't afford it, okay? X equals 25 would require, at the very least, 100 in income, which we don't have. So we need to look at boundary conditions instead, okay? Now, the boundary conditions will let us determine which one has higher utility. The two boundary conditions are x1 equals 12.5 and x2 equals 50. Okay, putting these into our equation, we can say that x2 equals 50 would give you 50 utility, but x1 equals 12.5 actually gives you 141 utility, or around that. So we would want to consume 12.5 of x1 because it gives us the highest utility overall. So that's how we did it. Okay. Again, if you're having trouble, feel free to look at the document. Feel free to pause just to go through what I've done. Okay. Then, if we have to minimize for this constraint, we have two different values. We have alpha equals a equals 2 and a equals 4 and a equals 2. Now, the first one is actually quite easy. If alpha equals 4, it's minimized at x equals 1, y equals 1, and I'll show you why. Because normally this is pretty tricky to understand for most people. Hold on, let me just check I'm still recording. Yeah, I'm still recording. Let's define our constraint. Okay, so we have, let's define our function that we're trying to optimize. So we have this function. I'm going to just set 1 as its diameter right now. And we're going to set our constraint. Now our constraint was 2x plus y is smaller than or equal to 4. Okay? Now, hold on, let me just... a squared. No, don't. I'm gonna have to do a constant thing. Here we go. Sorry, I'm just going to set up a little experiment showing why this is the case. Okay. All right. So at 1, 1, this is where our function. Okay, so if I move the radius down to this, okay. if the radius of this circle is 0, so if the value of this function is 0, it lies at 1, 1, right? And then as I expand it, the value of the function increases, okay? All right, so this is the absolute value. This is the amount of points that are valid, essentially. However, okay, you can see that our central point of the function, lies within our constraint already. Because at the minimum, our function already satisfies the constraint, and because we look to minimize it, not maximize, we're minimizing the constraint, at c equals 0, the function is already minimized, okay? Because I'm already at equals 0, which is the minimum value, and I'm all still within the constraint, okay? So I don't even have to change anything to make it work, okay? So if I put x equals 1 and y equals 1 into this, the standard default values, it would still satisfy my constraint. So I'm going to go with that, okay? This is what we call a slack constraint, basically where the initial point already satisfies it. However, with the next one, it's not as easy. You can see that our point now lies outside the constraint. So we expand it out, and we can see that 0.2 satisfies this. This can be done through the Lagrangian as well. So we're going to do a Lagrangian. We get the following, and we are deriving with respect to x and y, and we get 2x minus 2 minus 2 lambda, and 2y minus 2 minus lambda. Phrasing these in terms of lambda, we get lambda plus 1 and half lambda plus 1, and putting these back into our constraint, we get lambda equals negative 0.4. Putting these back into our values of x and y, we get x is equal to 0.6 and x is equal to 0.8, which we can see, hold on, one moment, which we can see is true, okay? Also, I've heard some people asking about what software I use. I'll put a list of software just sort of down in the description, okay? So I use Wolfram Alpha, I use GeoGebra, I use a few other things. These might be helpful in case you need to quickly search up something in the exam, so I'll put them down there in case you guys need it. Okay? Cool. So, yeah, that's that. Okay, so that is B1. Now, B2, I really had a tricky time with. The linearization bit is fine. The linearization can be found on, I believe it's something in the 640s. Just give me a second here. I'm just going to find a specific page for you. Where is it? Where is the linearization? Here it is. So if you look on 643, that is 643, you can get the sort of breakdown of the linearization. The basic thing is that a linearization looks like this, where you have the derived function, which is equal to A, which is the matrix you're timesing by, which is... Oh, wait, I should probably rephrase that, shouldn't I? Yeah, so how about we rephrase it for something that's actually in the book, just so I keep it clear. Oh dear, I copied something that I didn't mean to. What happened? Sorry, something messed up there. Did I copy? Oh, I probably should have done that. There we go. Oh, I just deleted the entire thing. That's fun. Yeah, hold on one moment. So, so I'm just going to redo another matrix here. And this one is going to be in terms of, yeah, so we need to do F1, F2, G1, G2, yeah. Okay, sorry, one moment. Actually, I'll pause for this because I don't think you guys need to see this. Okay, I'm back. Alright, so that's a better representation of it from what's in the book. So that's sort of the linearization of the system. It also says on page 644 that the solution paths of the linearization approach the solution, well, the stable point, if the eigenvalues of the matrix have negative real parts. Okay, so if it's like negative 2i, negative 2 plus I, or negative 2 plus 3i, that would be approaching the that. But if it has no eigenvalue as a zero real part, yeah, so if they have some real part, they'll go close. But if they both have positive real parts, no solution will approach. So if it's like plus 1 plus I, 1 minus I, that won't approach it. Okay. Now the next part, I couldn't get. I've asked around for people who could get this, and nobody seems to be able to. So let's just go over it. In a model of pollution, capital K and pollution P satisfies the pair of differential equations kt over dt, k sk to the power of alpha minus 1 minus delta, dp over dt k to the power of beta minus gamma p, where the following constraints exist. Find the fixed point k, so find this basically the stable point, satisfying k must be larger than 0 and p must be larger than 0, and show that it is locally stable for the nonlinear system. Find an implicit expression for kt, where k0 equals k of 0 equals k0, which is larger than 0, larger than or equal to 0, and find its limit as t approaches infinity. I can do this. I got stuck on the derivative when both derivatives have to equal 0. I know how to do this, but I can't. That's the thing. I know generally how to do nonlinears, but this nonlinear is quite tricky, and I couldn't quite manage it. If anyone else knows how to do this, please let me know. Okay, that's all I could really figure out. I'm sorry I couldn't complete B2. I can't really stretch myself that far. But yeah, hopefully you guys are having a good time revising. Hopefully you're not too stressed out. Feel free to text me if you have any questions. I am trying to get to them as fast as I can, but sometimes I miss a few, so I'm sorry if I'm the one you miss. You're the one I miss, I guess. But yeah, that's it. Hopefully you guys are doing okay. I'll see you later, okay? Bye.